We've seen with cars that software development involves conversation throughout an iterative process in which each member of the team can engage with the code for the upcoming software release. So far in the course, we've analyzed and specified requirements for internet architectures, network technologies, data management, even the software structure and flow. But what does it take to make software? Let's build on the insight from cars. Like all products and services, some steps take place for the software to come alive. These are part of the software development lifecycle. Analysis and planning is about the time and resources available, aligning the project goal with the company's larger mission, as well as cost estimation. We extensively touched already on different requirements from architecture to network and data. And then design and prototyping are not about aesthetic, but the functionalities and flows. How should the software behave? With software development, the code gets written, and then testing is all about ensuring the resulting code has the intended behavior. It is the quality check. Deployment means moving the code from an environment to another, commonly from development to production. Thus, it makes the software available to all users, releasing it on infrastructure with the appropriate resources to handle the expected number of users, for instance. Maintenance and update, the last milestone. It is about keeping the software running and collecting bugs and requests for new features, feeding the next cycle. These are activities to expect in software development. If you look around, you'll see many diagrams, primarily circular. We deliberately present a list to emphasize the actions rather than a particular process. As we will see, various mindsets and approaches influences these activities organization depending on the software project. It is crucial for everyone in the design and development team to understand how they develop a given software-based product. It creates a shared vocabulary for each step along the way. It defines communication channels and expectations between developers and project stakeholders. It provides a shared understanding of what a completed activity means. It prevents what we call scope creep, a term to describe features added to the project beyond the project scope. Then a shared understanding also formalizes how to handle bugs, feature requests, and updates. It sets clear goals and responsibilities for the entire team. The team. This is why we discuss this whole topic. As a designer, you take part of the design and development team of the software-based product. A strong product team brings together different specialized skills and responsibilities. There is a sense of ownership for a product or a substantial part of a larger product. There is no hierarchy. A strong team has a flat organizational structure. It is durable over time rather than just for a single project. Who's in this team and what are their roles? Well, let's start with the product manager. Deeply understands all aspects of the business, the market, the industry, the customers, the data, driving the evaluation of the product's success. She or he is responsible for what needs to be built, the so-called product backlog. However, she is not the boss, as this is a flat organization. In the past, As product designer, you would receive requirements and specifications from the product manager. Today, you work side by side on product discovery and in close interaction also with engineers. You develop prototypes and test with users. You design holistic product experience. It requires the literacy of all software-based product aspects, which you touched on module 1 to 5 of this course. The engineers make it happen. They are the developers who implement the software to fit the technical requirements such as robustness, scalability, or security. Through your Python programming assignments, you do not gain the ability to tell them what to do. However, you get the opportunity to closely interact with them and understand their perspective to elaborate an innovative solution together by joining strengths. And then we have data analysts who might take part in the team or be an accessible resource. Work in close interaction with them to get the data you need for your design insights. We know what activities we need to go through and who is on the team. We need to decide on how we go from the beginning to the end of the software development. It means defining the order of activities and how to transition from one activity to another. What shall we do next and for how long? This choice depends on the nature of the software-based product. How well do we understand the requirements? What is the expected lifetime, a relatively small project or one to last and be maintained for several years? What are the risks involved? What are the resource constraints? What are the needs for interaction with the stakeholders? What expertise do we have on the team? Depending on these questions answered, the process can range from top-down and linear, a more traditional approach, to bottom-up and non-linear. Let's take two examples, the Waterfall and the Agile model. The Waterfall model is the traditional approach. Linearly, each step is complete before moving on to the next, from designing to developing, testing, and deploying. Some Waterfall model includes more steps while the principle remains. There is a limited space for new ideas throughout the process, as well as little customers' involvement. We agree with the customers on what we will deliver early in the development cycle. We define the budget, the scope, and the time in the beginning. It makes planning and designing much more straightforward. We can develop the software entirely and more carefully based on a complete understanding of all software deliverable. It is easier to measure progress because we know the full scope of the work in advance. However, the development of software-based product takes place in a dynamic environment in which requirements evolve quickly. The customer rarely knows the specifics of what they want at an early stage of the project. And the time to deliver the project is lengthy, giving priority to documentation and completeness. The Agile model emerges from these challenges. On the other side of the spectrum, a non-linear bottom-up approach carrying four values: individuals and interactions over processes and tools, working software over a comprehensive documentation, customer collaboration over contract negotiation, and responding to change over following plan. This results in a design and development team adaptive to change, with shorter planning and commitment cycle, and focused on collaboration and interaction. Generally, this is a setting fitting today's needs for software-based product development. As we see on the slide, Agile is not a process, but a set of values expanding into this manifesto of 12 principles. Scrum is a framework of agile development revolving around sprints, which are development iteration of 2 to 4 weeks. The release of a new product version takes place at the end of each sprint. The team defines the tasks and goals for the sprint and sticks to them for that sprint duration. The key metric is the velocity, how much work completed during a single sprint. The team cleans up the board after each sprint and it suits long projects well with cross-functional teams. Kanban is another method originating from manufacturing with a popular board visual. We got a glimpse of that board in our discussion with cars. In contrast with Scrum iterations, Kanban is event driven. A change in plan can occur at any time, and the team can add tasks to the Kanban board as long as there is capacity for it. As explained, the process of discussing an update which the team can release as soon as they agree, leading to continuous delivery. With Kanban, the critical metric is the lead time, how long a task stays on the Kanban board up to completion. The complete history of tasks remains throughout the project and it suits shorter projects with specialized teams. It gives you a dry view of these two ways to work with agile development. But there are extensive resources available. I hope I tease your curiosity to try one of them in practice in your design projects. This is, to be honest, the only way to grasp it. As industrial design engineers, you will most likely work with Internet of Things devices with the additional challenge of combining hardware and software development. There are fundamental differences to keep in mind while setting up such a hybrid process. The lead time for tasks of each type will differ significantly, usually imposing two parallel iterations at different paces. The costs and tools vary, leading to a higher skill diversity in the team. Finally, hardware requires additional distribution and certification steps for each release. Iterations, small steps, evaluations, regardless of the software model our team decides on, it all comes down to balancing the risks and efforts. We develop prototypes that help us learn along the way at a much lower cost than building and testing the final product. It is what Marty Kagan captures in his book Inspired. What are the risks that can lead to wasted effort and resources? Well, there are value risks, whether customers will buy the product. Then usability risks, check whether users can figure out how to use the product. A feasibility risk looks at whether our engineers can build what we need with the time, skills, and technology we have available. Finally, business viability risk validate whether the envisioned solution also works for the various aspects of our business. It opens up the need for a whole range of prototyping techniques to remove uncertainty, thus reducing risks. Feasibility prototypes. Can we make it? How accurate and reactive would it be? Alone or together with engineers, it is critical to test your concept's feasibility because it will impact the outcome. Algorithm, performance, scalability, fault tolerance, new technology, and third-party components are potential technical risks your team must address. User prototypes. You are probably familiar with the wireframe prototype. Augmenting this wireframe with code enables you to test your user interaction further by simulating how your product would react and how this reaction impact your users. Live data prototypes. When dealing with data in a new context, we often have misconception regarding how the data will look, or no idea at all actually. As data is usually the primary driver of a software-based product, experiencing live data is critical to find its appropriate role in your design concept. The live data prototype also helps you collect evidence. And then we have hybrid prototypes. You might find yourself combining several of the three prototypes that I just presented. An example would be a Wizard of Oz prototype that enables you to better understand user interaction and at the same time collect live data. Let's take the example of an existing product, Gita. Gita is an autonomous suitcase that follows you around with your stuff. It is a complex software-based product that combines hardware with software, data, and network technologies. It evolves in the street, a complex and rather unpredictable environment with a non-trivial user interaction. So testing such a device at release time seems extremely expensive and risky on the three axes of viability, desirability, and of course feasibility. Although back to the development processes, we would only get a complete test at this stage. Let's think about steps that could reduce our effort and risk. Striving for just the right effort to deliver value, the lean approach promotes what we call the minimum viable product, the MVP. Literally, a prototype of the product providing only the bare promise which customers would buy in. For Gita, a minimum viable product would be at least one step back. As long as it can roll and follow us along, why would we go the extra mile if this MVP fails to convince our targeted user? Still, this MVP is far down the line. Many technical challenges need to be tested for this autonomous device to become a reality. What if we prototype a remotely controlled device? We can be the device brain with some Wizard of Oz steering its movement from a few meters away. It looks like a hybrid prototype. We get to confirm the feasibility of some technical parts. We collect insight from potential users as they immerse themselves in the situation close to the envisioned one. And we also collect data, a critical ingredient for training our autonomous device, by the way. Can we do a cheaper prototype while getting valuable insight? Indeed, we could manually push the suitcase, following the target user around. Through this step, we empathize with the object, the suitcase. We get its perspective so we can better anticipate what it needs to confront. And finally, following around the user with stuff in a bag could be the first step. How does that feel to be followed around by our stuff? Of course, there's the human dimension here. Someone is also following us, but very cheap and with great potential to generate insight about this future relationship between the user and the suitcase. There's a whole spectrum of possible prototypes. At each stage of the development process, it is critical to identify the ones that will remove as much uncertainty and risk as possible with the minimum effort. That concludes this first lecture on development methods. In the knowledge exercise, you will get the opportunity to practice this iterative search for the appropriate testing prototype. In the second lecture, we give a closer look at development practices.